Hello everyone, welcome to lecture 7. In this lecture, I will talk about the probability and randomness in the Python. I will talk how we generate random numbers in the Python and also how we can generate random number from a probability distribution. So in this lecture, I will talk about the randomness and let's see some application for the randomness to see how we can use randomness in the algorithm. So the randomness is a core operation of many commonly used algorithms. For example, if you have an algorithm for encryption of your data, and you have some data and you want to encrypt the data and send it to another person, you need to generate a random key and then encrypt your data and then send it to another person. For example, another application is the randomized storage that, for example, in the Python, we have a random hash table that used in the Python dictionaries, or approximate integration that we look at this later. And also another one is the randomized experiments and in randomized experiments, we need to generate some random number to do some operation on your data and then make an approximation of your algorithm. And for statistical modeling, you need to evaluate your model, for example, or approximate interface or approximate estimation. For example, you have a model that you need to interact with the user to see the reaction of your algorithm. You need to generate some random number as a simulation of the user and then see the reaction of your algorithm in different situations. And also we have lots of other randomized algorithm. And for the first one, we need to know that the source of the randomness. So most of the function we will see today sample from an interesting probability distribution by sampling a uniform random number. Then we apply some transformation on that and to generate the probability distribution to sample from another probability distribution. So for example, if you need to generate a sample from a probability distribution, at the first you can generate a uniform random number and then apply some transformation on that and then get the output. So if we want to do that, at the first we need to generate a uniform random number. How we can do that? And there are two main methods for the source of the randomness. The first one is that harvested natural randomness, and the second one is pseudo-random number generation. So let's see two main methods, and the first one is the natural randomness, which means that we have a natural randomness from some natural phenomena that are sufficiently random because of physical entropy, that we can assume that they are random. For example, when a beam of photons is directed at a semi-transparent mirror, the photons will randomly be reflected or transmitted. This means that we can consider these photons that are transmitted or reflected random. They are treated in a random way. And there are lots of other phenomena that we can consider them as a random phenomena, for example, electromagnetic fluctuation in a vacuum, or other example in the nature. And also this is important in different phenomena. The rate at which this can be harvested may be limited. It means that the rate is different in different phenomena for the generating random number. or random operation or something like this. Another one is the pseudo-random numbers that we need in this course, and the pseudo-random number generator return a sequence number that has the statistical properties of a uniform random sequence, but it's actually deterministic given an initial value. This means that we can generate some random number by giving an initial value or seed, but actually if we have the seed and initial value, these numbers that we generated are deterministic, means that we can generate a random number again and again and again by having knowledge about the initial value. So the initial value is called seed, and then without knowledge of the seed, the sequence that we generate should look random. And so this means that we have an algorithm to generate some random number, but this algorithm gets some initial value. And if we know the initial value and also have some knowledge about the algorithm, we can generate the number that we just created. This means that the number that we just created is not random. But if we don't have knowledge about the initial value, the sequence that we generate look like a random number. And also in this case, we can generate many such sequences because we can generate this sequence by different initial value, and then we don't have any limit on the initial value. And also, given the seed, computing pseudo random numbers is extremely fast and effective because these algorithms are so fast to generate lots of random number. So let's see an example in the Python. We have a module in the Python which is random, which called random, and then for generating some random samples from some distribution. And also we can sample from a sequence by using this module. I show an example here for the random module. For example, at the first, in the top of your script, you need to define random.c and passing a number to that. And after passing this number, you can generate random number. But for example, if you have a number for the seed and as an initial value, every time that you run the program, you get the same random number. But if you want to get a different random number, you need to change the initial value or the seed. For example, here, if you have random.c42, and then call a function which is random parentheses, we get this value. And again, if we have again random.c42 and then call this function again, we get the same random number. This means that you need to change the initial value if you need to get different random number. And the function that we just called, which is random parentheses, generate a random uniform random number between 0 and 1. And you can also generate random number from different or specific distribution. For example, here, we generate a random number from Gaussian distribution by calling this function and then pass the mean and the standard deviation to this function. Because this distribution should get mean and standard deviation to make the distribution. And then we need to pass these values to get a random number from this distribution. You can see the documentation of the random module in the Python to see the function that we can use, but For example, another one is the expo variate. And the expo variate is a function to generate random number from exponential distribution. And in exponential distribution, we need to pass lambda, which is the mean of this distribution, which is 2, and get a random number from this distribution. As I mentioned here, you can also randomly sampling from a sequence. For example, we have a sequence here, red, black, green, and we need to sample from this distribution. So we need to call this function traces and then pass as a first parameter the list that we want to sample from that. And we have another list here, which is the weight of each element that we have in the first list. For example, 18 is the weight of the red, 18 is the for the black, and then we have 2 as a weight for green. You can convert these numbers to probability between 0 and 1 to see the weight of them by, for example, 18 divided by sum of them, which is 18, 18, and 2, and see the weight of the red, right? And this means that in most cases, we choose between red and black because the weight of the green is much less than them. And also we pass another parameter here, k, as a 6, which means that the number of samples that we need to get from this list. So in the output, we have 6 samples from the list, which 3 of them is black and 3 of them is red because the weight of them are much higher than the green, and the weight of these 2 are same. So in most cases, we get these 2 in the output. And also randomness is implemented in the NumPy, and for example, you can use np.random, and then we have the same function in the NumPy, which is np.random.c, and pass the initial value to that. And we have a function in the random module in the NumPy, which is the rand, and then we pass the number of random number that we need to in the output, which means that we need 5 random number in the output, then we pass 5 to this function. And you can specify the distribution that you want to get from random numbers. For example, randn generate random number from a normal distribution that the mean of the distribution is 0, and then the standard deviation of that is 1. Which means that the normal distribution by mean 0 and the standard deviation 1 can generate negative values. So in the output, you can see we have positive and negative values. But also, for example, for this one, we get the value greater than the 1, but it's possible in the normal distribution with mean 0 and 1, standard deviation 1 to get the random number greater than 1. If you want to change the mean and the standard deviation of the normal distribution, you can do that with this line. Here, we multiplied each number that we get by 0.5, which can be the standard deviation that we need, and also plus 3, which means that the mean of the output should be the 3, and the standard deviation should be 0.5. So in the output, you can see the number that we just generated are much higher than the previous one. because we just plus 3 them, and in this way we just change the mean and the standard deviation of the normal distribution in the output. Also, if you want to generate random integer number, not real value, but integer value, you can call a function randint and then pass a start and the end, a start point, end point, and the how many numbers that you want in the output. So we get the 5 integer value between 0 and 100 in the output. So for this course, we need to review random variables and probability basic. Let's see a definition for the random variables. We show random variable with capital letters, and for example here we have a random variable x, which is a quantity that can take any value from a set of possible values omega based on a set of probabilities. So for example, imagine we are flipping a coin, and in this case the random variable is the outcome of the coin flip, and the possible outcome are or omega are h and t, which is head and tail. And also, as you noticed, we have a set of probabilities for the outcome, which can be here 0.5 for the head if we have a fair coin, and 0.5 for the tail. And we have a kind of random variable, which is the discrete random variable, which can take value from a finite or countably infinite set. And the value that we can take for the random variable are discrete. And the example of this kind of random variable is the outcome of a flip coin, can take one of 2 possible values, or a randomly dealt 5-card poker hand can take one of the 2.6 possible billion values, but they are discrete. And also the number of people who log in to Netflix between 1 p.m. and 2 p.m. also can be any non-negative integers. It can be 0, 1, 3, 2, 4. And also the end of season goal differential for a soccer team can be any integer, positive or negative, but the only limit that we have here is that the outcome values should be discrete. It can be negative or positive. Another concept that we need to know about the discrete random variable is probability mass function. And the probability of each possible outcome is defined by a probability mass function. For example, for flipping a coin, we need to know the probability of outcome, which is tail and head, how many times we can get the tail and how many times we can get the head. So for a discrete random variable with supported omega, a probability mass function or PMF is like this. We get the we get all possible outcomes and generate a number between we get the number between 0 and 1 that map possible outcome to probabilities. we have two conditions that we need to satisfy in the probability mass function. The first one is that probability of any single outcome must be between 0 and 1. And the probability of all possible outcome must sum to 1, which means that we get all the possible outcome and get the probability of that, and we get the summation over them. And then the summation of them should be 1. Let's see the example of the probability mass function. And for example, we have a dice, and let's X represent the outcome of a 6-side dice roll. So in this way, the possible outcome, the set of possible outcome is 1, 2, 3, 4, 5, and 6. And then if we assume that the dice is fair, then the probability mass function should be like this, that we have a probability 1/6 for all of them, because the dice is fair, and then the summation of all of them should be 1, which is 6 times 1/6, which is equal to 1, and also 1/6 is between 0 and 1. Another example for probability mass function. Also, you should notice that the outcome value are discrete values here. That's why we need to use probability mass function here. And another example is the number of people entering a central bank between 1 p.m. and 2 p.m. So the possible outcome here is all non-negative integer 0, 1, 2, 3, 4. And then also we can see we can name this distribution as a Poisson distribution. And so probability mass function for the Poisson distribution is like this, that we need to specify a lambda, which is the mean of this distribution. So if the lambda or mean is equal to 1, we can see that the probability of the 0 and 1 is much higher than the other, and then drop by increasing the k, which is the number of people that come to the bank. If you change lambda here, you can have a different distribution, but they are all are Poisson distribution. So here also note that we use probability mass function because the number of people that come to the bank are discrete. And we can use the Poisson distribution for this. The Poisson distribution is an example of parametric distribution, which means that to specify the distribution, we need to pass a parameter to this distribution, for example, here lambda. So it requires a set of parameter values to fully specify the distribution. For example, the Poisson distribution is like this, and then after getting lambda, we can compute the probability of x by this formula. In this case, the distribution has a single parameter lambda that must be positive real number, and then much of the statistics is concerned with inferring this parameter from the data, which means that you need to have your data, and then you need to calculate the value of the lambda from the data, and then have the distribution like this. So until now, we talk about the discrete random variable, and now we want to continue on the continuous random variable, which means that the value that we can get for a random variable are from a set of numbers uncountable and infinite set, such as a real number. And the example that we can have in the continuous random variable are from the, for example, here, the height of a randomly selected person, or income of a randomly selected household, or the amount of time between hard drive failures in the server. So in this case, the value that we can get for the random variable is from real numbers. So for discrete random variable, we had probability mass function. For the continuous random variable, we have probability density function. They are so similar to each other, but let's see the example definition for the probability density function. So the distribution over possible value of a continuous random variable is given by probability density function. So given x, which is the continuous random variable, the PDF or probability density function describes the relative likelihood of the continuous random variable taking given value. So a PDF must satisfy the following two conditions. The first one is that all values must be non-negative. This means that the probability of a given x should be higher than 0 or equal to 0 for all possible values. And also the area under the PDF must be equal to 1, which means that if we get the integral over all the possible that values and get the PDF of them should be equal to 1. The probability of x falling between a and b is given by an integral, obviously between a and b, and we can show the probability of the x between a and b by integral a and b and px dx. So, for example, we have a uniform distribution between a and b. So, in this way, the all values that we have in this range has the same probability. For example, 1 over b minus 1. This is because after getting integral between a and b, from this value we get a 1, which can satisfy the second condition that we had here, right? So as another example for probability density function, we have normal distribution. Perhaps the most common distribution in the statistic, which is normal distribution. So normal distribution takes two parameters, a mean parameter and a variance parameter. And then given these values, we can specify the probability of x. And you can see the normal distribution with different inputs of mean and variance here. So another useful concept in the in probability distribution is the cumulative distribution function. And this can be for continuous variables and discrete variables. So consider that we have a distribution for random variable x, distribution px over a random variable x. So the CDF or cumulative distribution function give the probability of the probability that x is less than some values. So, for example, if you want to compute f, capital F x, this can be equal to probability of x is less than this value that we pass to CDF, right? So for the continuous variable, we can compute CDF like this. We start from minus infinity until the x, and then pass the we get the integral over the probability that we have for each value. I think that would be x, not x prime. And for the discrete variables, we have a same formula, but instead of integral, we have a summation over all the possible outcome from minus infinity until the x. Also, x also is included here. So, as an example of CDF, consider that we have a multinomial distribution, for example, for a 6-side dice roll, and the outcome can be 1, 2, 3, 4, 5, 6, and then the probability of all of them are same. So CDF of x is equal to probability of x, capital X less than x, and then we have a summation over all the possible values. So if you want to know that what is the CDF of 3, then we have the probability of a capital X less than 3, and then we have for the we have probability of x is equal to 1, which is 1 over 6, and x equal to 2, which is 1 over 6, and then we have finally is x is equal to 3, which is 1 over 3, well, 1 over 6, and then we have 3 over 6. We get the summation of them, and then after simplification, we have 1 over 2 for CDF of 3. This is an example of the CDF, and then we need to know something about the expected values. And if we want to have an intuition of the expected value in general is kind of average or mean, but a common computation we're working with probability distribution is expected value. So let's see a definition of the expected value. So given a distribution px over a random variable and a function of the random variables that generate an outcome for all possible values that we can get for a random variable. The expected value of the function is defined as a e of f(x), and then we have a integral, and we get the integral over all possible values that we have. And we get the probability of x times f(x). And this is the definition of the expected value. We get the x, and then we just get the f(x), and then what is the probability of the x. Where the integral is a sum, then x is a discrete, because this is just about the continuous, and then we have that also for the discrete values by summation instead of integral. So expected value, as an example, we can see that for the multinomial, and so let x be the result of a 6-side dice roll. So in this case, what is the expected value of the x? Expected value of the x is the summation over all possible values that we have, and getting a probability of that, and then times exactly the thing that we have here. Because here we had fx and we just replace that here to generate the expected value. So because we have x here, we just replace that here, and we get the summation over all the possible values, which is 1, 2, 3, 4, 5, 6, and all of them are the same. They have the same probabilities, which is the 1/6, and then we have a summation over all x values that we had, and then this is the expected value of this multinomial problem. So if you want to compute the expected value of a normal distribution, right? So it doesn't matter, we can do that also by getting an integral, and we just replace the x square here, and this is the probability of x in normal distribution, and after some simplification we can have this formula, but it doesn't matter. It's just an example to show that how we can compute the expected value in continuous variables, random variables. So a concept that is useful in the computing expected value is the linearity of the expectation. So consider that we have nx n random variable, which is a collection of discrete random variables, and let x is the summation over all these x's that we have here. Then the expected value of the summation of them can be considered as a expected value of summation over all them, and because the linearity of the expectation property, we can take out the summation over the expected value here to generate this formula. So if you want to get an expectation value for the x, we need just to get the summation over all discrete random variables that we had here. So for example, let x be a result of a six-side dice roll, and x2 is the result of the rolling the same dice again. So if we want to have another variable, which is x is equal to x1 plus x2, what is the expected value of the x? And this can be right by this formula x. Expected value of the x is equal to the summation of all the expected value that we have for each random variable, which is 3.5 plus 3.5, which is 0.7, because we already compute the expected value of the one paired six-sided dice roll here, which is 3.5, and then we can compute that by summing over all two possible values. So in most cases, the expected value is too complex to evaluate, because as you notice, if you want to compute the expected value, you need to compute this integral. So in most cases, computing this integral is not easy and can be so complex. And there are so many reasons to make the computing expected value complicated. The first one is the normalization constant of the distribution, because in most cases we need to compute, we need to convert some terms. some values to a distribution, and then we need to normalize them by some of all of them or something like this. So this normalization can be make the computing the expected value difficult. And also another reason that I mentioned here is that maybe there is no analytical solution for the integral, and the computing the integral can be so difficult in some cases. And in these cases, we need to use an approximation instead of computing exact value of the expected values. Type of approximation that we can use are, for example, the approximated distribution with a simpler one that allows us to take the expectation that can be, for example, variational base, or we can compute the upper bound or lower bound of the probability distribution, and then compute the expected value based on this upper bound and lower bound, which can be example of that variational approximation. And another approximation is the sampling-based approximation, Monte Carlo integration. And this is the method that we need to study more in this lecture, because this is a so simple approximation and can be so useful for computing the expected values. So let's see what is the Monte Carlo integration. Monte Carlo integration approximates an expected value by sampling from the associated distribution and then taking an average. What does it mean is that, let x be a random variable from a probability distribution px, and let fx be a function of the x, and we get some sample from these random variables, for example, as 1, 2, 3, until up to s, and we can sample these we can sample them from probability distribution px. So expected value of the fx, if we want to compute this, we need to get an integral of px fx. But instead of that, we can just get some sample and then get an average of the samples. So in this way, we can compute the expected value without computing the integral. So this is so simple. So for example, suppose that we have x coming from a normal distribution for mu, which is equal to 10, and the standard deviation is equal to 2. So in this case, we want to know what is the expected value of x squared, and the probability of the x is equal to normal distribution like this, and fx is equal to x squared. So if we want to compute the expected value of the x squared, we need to get some samples from the normal distribution by passing mean as a 10, and then the variance as a 4, and then we get the average over all the samples that we get to expected value for this one. Yeah. So if we want to do that in the Python, we know that we already saw that we can get a random variable from normal distribution from NumPy by calling this function, right? So np.random.randn can generate 1,000 numbers from normal distribution between that the mean is 0 and then the standard deviation is 1. So if we want to generate random numbers from normal distribution by mean of 10 and standard deviation 2, we can generate 1,000 of them and multiply them by 2 and plus 10. This can generate 1,000 random number from this normal distribution that we need here. And then we get we get the squared of them by this part of line of the code, and then we get the np.mean, which is the average of them. So as you can see, this is the expected value of the x square by this normal distribution. So you can change the number of samples and getting better estimation. But as you can see, if we generate lots of random sample from normal distribution, here we get a close number to the previous one. So this is so simple to get the expected value for a variable that we need. So another concept that we need to know before working on probability distribution in a Python is working in logspace and a trick which called logsumexp. So let's see that what are them, and so consider that we have lots of distribution that need to have some exponential of the values that we have in the distribution. For example, if you are using exponential distribution, you need to get e power of something, right? So exponential for the even moderate values can result in numerical overflow or underflow, which means that we have some limit on storing numbers in the computer. For example, we have 32 bits or 64 bits. So if we have a large number and we get the e power of this large number, this can get these numbers can be so large, and then we cannot store the number in 64 digit or something like this. So this can be an overflow. And same as this, if we have e power of minus something, which is a large number, this can be so close to the 0, and we cannot store these kind of numbers, and this should be considered as an underflow. So if we have this problem in our code or our program algorithm or something like this, one common solution is to work in logspace. What does it mean? So as an example, consider that the distribution of multinomial distribution, which is the standard distribution for finite set, and consider the following multinomial distribution over k discrete values parameterized by a length of k vector of weight alpha. So if we want to compare the probability of x is equal to one of these numbers, for example, 1 to 0 or something like this. And given the rates that we have for each one, we can compute that this probability by e power of each value that we have for each element, and then get the divided by the summation of them. So as I mentioned, this e power of something can be a problem in the overflow or underflow. So rather than evaluate this function directly, which can have a risk of over or underflow, we can evaluate the log of P and F probability mass function for this one, which means that we get the log from this one. And if we get the log from this one, we have log e power of alpha I, and then minus, because we have a division here, we have minus here, minus log of summation over all e power of a alpha. And this can show that this trick can solve the problem, but why this is happening? So so we have this if we get a log from the probability, and we have this. So computing this log, which is the second part of the formula, is also known as known as a convolution function. And this also can have a problem with e power of something, because as I mentioned, e power of alpha can be a problem. So we also have this e power of something here. Also, this can have another problem. So to solve this, we get another variable here, which is alpha star. And alpha star is the maximum value that we have for the alpha I. So we can use the following trick to solve the problem. So log of summation over e power of alpha can be write as a log of e power of alpha star divided by e power of alpha star, which is equal to 1, which means that we don't add anything to the formula. And then we separated this two by taking this denominator to the summation, and then we have, because this is the denominator, and get a log, and then e power of alpha I divided by e power of alpha star is equal like this, and then we plus to this log of e power of alpha star. So if the base of log is e, we can write this as alpha star, and then we have log of summation of e power of alpha I minus alpha star plus alpha star. So the problem can be solved here because the alpha star is the maximum value that we can get for all alpha i's, and which means that the maximum value that we can have here is if alpha I is equal to alpha star, this value can be 0, and then e power of 0 is 1. and then all other possible values are less than 1. So in this way, the e power of something cannot overflow. Right? So in this case, this can solve the problem. And also because we have just alpha here, we cannot have the problem here because we don't have e power of something. And also we solve the problem with this, the second one, by this. And also the underflow cannot be a problem here because now we are going to that the largest term in the sum is equal to 1. As I mentioned, the largest value should be like this, that the alpha I is equal to alpha star, and then we get a 0 and e power of 0 is 1. And then there cannot be overflow, and individual term in the sum may underflow, but we just need to consider them as a 0 or something like this because this result only in round-off error in the final sum. Because if alpha I is equal to something so low, then the e power of something minus alpha is equal to close to 0, and we just need to consider them as an error in the final sum. And so important that we know that the log sum is implemented in this module, SciPy, and then special, and then you can use log sum exponential here. The reason that the name is log sum is that we have a log, and then we have a summation, and then we have exponential. So they name it as the operation that we do on the alpha here, log sum and exponential. So consider that we need to do this trick on the Python, and we have this probability distribution, which is a multinomial, and then we need to compute log of this probability distribution, which is kind of alpha I minus log some exponential of alpha. And then we just need to pass alpha from 1 to up to k to this function that I mentioned here to compute this value, and then pass alpha I minus this value that we just computed by this function. So from this module, we import this function, log sum exponential, and then we have a one-dimensional array as an alpha I. For example, alpha 0 is 3, alpha 1 is 4, alpha 2 is 7, and alpha 3 is 2. And then we need to find the log probability is 1, which means that we need to know what is the probability of x is equal to first one. And then we need to compute that by passing alpha 0 in minus calling this function, and then pass the all possible alpha that we have in this array to this function. So after that, we store the value in this variable, and then we get np.x exponential of the value that we just created by this function. The reason is that we just in here we just compute a lot of probability distribution. So if we want to know the probability that we need here, we can get the exponential of the value that we have here, which can be this one. So this is all that I need to talk about this in this lecture. So if you have any question about this lecture or assignment 3 or the project, please send the post on Piazza or email.